nanohub.org.
Online simulation, and more for nanotechnology.
Today's talk is going to be on fabrication, nanotechnology fabrication. And it's going to be done by Terry or Terrence Kuzma is his formal name, but everybody goes by Ter. And he's an assistant professor here in engineering science and mechanics, and teaches at the undergraduate level, but also at the graduate level coursework in engineering science and mechanics. And he's been here for 173 years, I believe, within the department. He can tell you more. But he's been here for quite a while, and he's taught like 1,000 students in this curriculum, basically somewhere around 1,000 people in this one curriculum that we're teaching right now, 18 credit capstone semester that we teach this at Penn State. So, Terry, I'm going to turn it over to you. Terry Kuzma, as again, he's our elite professor for our program here at the capstone semester at Penn State. So,
this is my. So they asked me to give like a picture of my presentation. So this is the picture of my presentation, and a picture's worth 1,000 words. This is what I'm going to present today. And as Bob alluded to, they said, who wants to do all of manufacturing and nanotechnology? Raise their hand. No one did. So then they said, you do it. So I got volunteered because nobody else wanted to take on the topic because it was too big. So anyhow, I'm the volunteer because everybody took a step back and I stood still like on TV. So I'm the guy that got to do one that has 1 million questions. So I think that's cool. We can just make this like interactive. If you want to have some questions or whatever, that's fine, because I want to go over all of like top-down manufacturing and all of bottom-up manufacturing. And that's kind of like, it's insane to do in, an hour or whatever time limit. But one of the things is it acts as a milestone or a marker or a platform that you can ask questions about other things we've seen in nanotechnology. And this more specifically would be, and what I think that I do and what I contribute to my students, I do nano manufacturing. So that's interesting, because if you would look at that concept, for me to make stuff on a nanoscale, I have to know about the nanoscale and the applications, say like an artificial knee, or a screw for an arm, like when you break your arm, or for a microprocessor. I have to know about those applications. And when I know about the applications, then I can begin to use the tools, the manufacturing tools that work in the realm of nanoscale assembly. Does everybody see that? So there's really two basic types of nano type of assembly. If we want to look at it that way, we can make a slice. And I think that's good engineering, is always divide and conquer, like break things down. We could say that there's two formats in engineering and nano manufacturing. And there's a gray area there, and you mix them up and it depends. But there's basically, a lot of people would say there's top down and there's bottom up. And that's nice, because it's like heads and tails, yin and yang, two different things, right? So what we're looking at with top down, maybe, which would be a classic example of that, is my picture on the left. The picture on the left of your screen is a transistor. So that's a metal oxide semiconductor, an MOS transistor. Often you would see words like CMOS, which would be complementary MOS transistors. So there's this, I guess, tone of a transistor to where we see the substrates P-type and the wells are N-type. So that's a certain kind of transistor. It would be paired together spatially with another transistor, and the substrate would be N-type and the wells would be P-type. So it would be actually just like that, like heads and tails. It would be complementary, that they're exact opposite. So interestingly, and maybe trivia for you guys, why do they have CMOS, or why is that a word, or what does CMOS basically do for us? And it stands for complementary MOS, metal oxide semiconductor transistor. And that's what this is. But this is a single MOS. not a dual one, because then it gets a little bit confusing, the picture. So I put on like half of the basic transistor. But this is a transistor and it works good. The twin to that, or the mirror image to that has the opposite dopant levels in there, that works good too, and they're good transistors. But the problem with them, or I guess the trivia here is, if you had one transistor and you used it, when you turn it on, it takes a lot to kind of like shut it off and turn it off. And we want things to be fast like this: turn off, turn on, turn on. It's kind of like sluggish to turn it off, and it might stay on. Does that make sense? So it's interesting, and maybe that dichotomy thing, like opposites. One acts as the gas pedal, and the other one acts as like the brakes. So why they have like two transistor systems, there's a lot of reasons, but the main reason is it turns on and off real quick. Does that make sense? But basically, if you could build this one, you could build the other one, or the ones that are put together. And this is an example of top-down manufacturing. So what's top-down manufacturing? It's really, probably nature doesn't want to do that. I'm just paraphrasing. You probably want to like trick nature into doing rather odd things and apply a tremendous amount of energy and start with like a big macro piece of metal or something and break it down into like atomic level deposition. That would be top down. Does that make sense? So we start at large pieces that really don't want to be put together somewhat. And then as engineers or whatever, we force them together with a tremendous amount of energy. So this transistor probably saw plasma processing, high temperature steps, who knows, infrared, all kind of energy things at temperatures that are like, would like make a roast chicken in your oven turn to dust rather quick. So we'll run at temperatures that would, melt aluminum or something like that, like 600 degrees C or 1,000 degrees Celsius. So these temperatures on here are just like crazy, but we're trying to like force things to happen that normally don't happen. And that would be, in my mind, an overall like discussion instead of just a definition from, Merriam Dictionary on, what is top down. So top down is, us forcing materials into certain positions with probably a lot of energy and start maybe from bigger entities and then pushing them into smaller entities. And that would be example of top down. And certainly probably, I'm told, the thing that you own the most of as a human being in the Western culture is transistors. So in your cell phone, it has billions of transistors in there. Does that make sense? And interestingly, if you would look at the size of the transistor that's sitting there, it's the same size as the COVID virus. That's kind of crazy. So in and about, they're in the same ballpark. Does everybody see that? So the thing that's kind of amazing, maybe not, or maybe interesting, I should say, is that, mankind or engineering or the desire of the economy is to be able to produce things that are on the scale of a virus. So understanding of viruses, or the ability to see viruses, because we want to be able to see transistors, because everybody wants to pay $1,000 for an iPhone. So we have that ability to do that. Does everybody see? So now I think it's interesting. I mean, just chemistry or biology or whatever, it was beyond the ability for people to grasp because it was so small. And it was certainly beyond the ability for people to grasp because it was so small, because there wasn't a lot of money really driving it. But when we came up into the semiconductor revolution, like in the 80s and the 90s, where people started saying, hey, a computer is a good idea and everybody has a cell phone, I better get one too. There was a real driving force into having the machine shop of being able to make transistors, et cetera. What did that do, interestingly, for biology? It kind of brought those people out of the mortar and pedestal days into like the semiconductor manufacturing era of the latest groundbreaking technology. So maybe, for example, it was really hard to find an SEM, and they weren't that good and they were rather expensive 30 years ago. Now they're like in high schools and they're all around, and for their performance, they're rather inexpensive. The same thing, I guess, with, I don't know, 15 years ago, like Bob says, time goes quick. I can't remember, but I went to go buy a atomic force microscope, and they were $250,000. And that was about what you wanted to pay to get one that was fairly good, but a desktop model. And then within 5 years, they were about 60,000. And then they stayed at that level in some senses. So there was like this breakdown of, the technology and the demand and the ability to manufacture and the cost sharing came to that, SEM's unattainable, AFM's unattainable. Now everybody could have them. So now you could get one and use it in your biology thing. And then people adopted different techniques to examine like cells or whatever. So really the driving force is always money for technology, right? But the money driven from semiconductors really helped out for the world of bio. And it was interesting when I started teaching the NMT program or nano manufacturing. It was actually called the semiconductor manufacturing program when I started in about 1999. I didn't have any biology students at all. It was all male, and it was all mostly electrical engineering. Then I taught and I started learning biology myself, and I went back to school and I took like molecular cell biology and courses on that, and biomaterials. My daughter works in that area too. And so I took all these other classes, and then I started getting more and more bio people. And I'm like, I think bio's going to really match with semiconductor nano. And then it grew. And now I would say, in some senses, on a given year, there's more people interested in the bio aspects of nanotechnology than the electronic aspects. And everybody knows what money's contributed from electronics, right? It's one of the hugest industries in the world. So that's very, very interesting. And I'm really proud. Well, I'm glad that I had a guess that I should go back and get some bio kind of stuff in my head. So now I actually teach, amazingly, graduate level classes in bio nano manufacturing. And I wouldn't have done that unless I had a little bit, I guess, luck and insight that I should go to other departments within Penn State and learn those fundamentals, and then what I knew about semiconductors. So what does that story have to say as a story? I operate in the machine shop of nanotechnology. What should I be able to do? Well, I can make stuff for the military. I can make stuff for Apple. I can make stuff for the food industry. I can make stuff for the biology, the pharmaceutical. It's very, very valuable. That's what I'm really into. What can you do as a machinist? The answer better be make almost anything. And if you have a bio person and they're really smart, because there's so much to know in bio, if you open up the doors and say, these are the manufacturing methods that you need because you work on a virus scale, they're delighted by that. And it's really, really good. So it was a leap, but not too much of a leap to understand semiconductors and then to make prosthetic devices like artificial knees and hips. So maybe this is why you took a conference, is to hear a discussion like this, because you often don't see these things written in a book. So it's kind of neat that I'm looking at top down and bottom up, but the commonality between them, like the ability or the need to have an SEM or a AFM or UV Vis, those kind of characterization tools to see what I'm doing, that's shared between like microelectronics, sensors, modern manufacturing, what optics, maybe artificial eyes or lenses for eyes or whatever. Those things are all shared together. So I'm again, lucky that I made some of the decisions in life and it led me to the right, or at least a satisfying place, that these things come together, so I think that that's very interesting. So I don't want you to look at this. It is a diverse presentation today, but really to me, they're a lot common. So I wanted to give you that message in the beginning. The drawing on the right is actually something that I teach the students to make in the course and have been for maybe 10 years. It's like a liposomal body, and it basically emulates the cell membrane that's in your body. So it's real bio-friendly because it's actually like a clone of your cell. But a cell in your body, and this is a lie and wrong and a bad number, but it's like 10 microns. Does that make sense? A blood cell's 7.5, but it's a Frisbee. You got neurons, you got all kind of other stuff, white blood cells. But we're just going to say 10 microns, 10 to the minus 6, 10 to the minus 6 meters, right? So we're going to say it's in and around there, in and around that platform. These liposomes are the scale, exact scale, and they're the drug for COVID. Liposomes are the drug for COVID, and they're also the virus. And those things are 100 nanometers or 80 or 60, somewhere in ballpark like that. Does that make sense? So you may or may not know this from watching these presentations or other internet things, but basically we're fighting the COVID virus with another COVID virus, but we put different, it's like a jelly donut. We put different jelly in the jelly donut. The COVID has RNA replication as the jelly, gets into your cell and says, make more viruses. And then your body freaks out because it shouldn't be making more viruses. And then your body, it'd be a good idea to have antibodies. It wouldn't overreact. So that's a problem with the COVID virus is it's a new virus and the body doesn't know how to take care of it. And it goes ballistic. So you get what's called a cytokine storm. And then your body gets bad things happening to it, especially in the lungs, kidneys kind of area where you're rich with ACE2 receptors. But anyhow, what we do is we make an artificial virus and we don't put in the RNA stuff that the COVID comes with. We actually put in, tie up the RNA like tie wraps, like just, defeat the RNA. So we actually deliver a shutdown switch with an artificial virus. And that's the COVID drugs that are commonly available now if you're willing to take them. If people are getting, I guess, immunized, they call it. I think more immunization would be of the antibodies. So the RNA modification drugs that they're offering now, that's what you would put an RNA modifier as the load in there. And that's showed as the hydrophobic moiety. I can't say it right now for some reason. Oh, let me get a drink of tea, then it'll come to me. Moiety, I think that's it. So anyhow, this model down below is actually the model of this liposomal drug, and it's real bio-friendly because it's made as like a subset of the cell that are membranes of our cell, and they call that a lipid bilayer. And then what we can do is we see on that outer core, there's things that look like springs, et cetera. That would be the corona part of the virus that we're experiencing now, the pandemic. And what that does is that's like Velcro that sticks to other things, specifically some type of other Velcro. And what we're interested in, at least from the aspect of COVID, it has proteins on that other core that would go to something called an ACE2 receptor. And they're like a garage door opener. And that protein would go there and say open. And then the cell opens up and takes in the virus. And then when the virus opens up, inside that virus packet opens up, and inside the jelly in the jelly donut says, make more viruses. The cell itself is a manufacturing entity, and whatever comes into it, when it opens up that packet, like a protein or whatever, the communication thing, it says, hey, take me to your ribosomes, and I want you to your endoplasmic reticulum. Take me there, and then I'm gonna produce what you tell me to do. This program, and the program is this RNA snippet, right? This little section RNA, and it happens that the COVID virus says make more viruses, but you could be doing things like make blood clotting material. Like if you cut your hand, you'll send out a signal, it'll be transported, and it'll say, hey, time to turn on the machinery in your body to make blood clotting because I have a cut, or other things, digestive juices, or whatever other life functions you need to carry out. The body takes in this information, and then your cells manufacture and do what they're told to do, as the jelly in the jelly donut is the program. Does everybody see that? That's what we're talking about here. So interestingly, in my course, we're trained, and I have labs, and you're welcome to have the labs. They're virtual labs, and it shows how to make those. And people have been making these, and one of the probably more abundant resources that they make that for, it's not for viruses or anything. We actually would put in a poison as the jelly, and then we make the system work. Well, it works by size. If you're in a cancer region, a lot of the cancers, not all, but some cancers in their cell structure, your cell structure is like shingle roof. It's an overlapping thing, right? So these are your like endothelial cells, and they overlap like that. But a cancer grows so fast that there's gaps in there. It's like a leaky roof. Does everybody see that? It's like a roof that you had a tornado and it blew some of the shingles off. Well, what's going to leak in there is not rain. It'll be these liposomes. So then the liposomes go through your healthy part of your body, and it has good vasculature and it's sealed. So none of that drug actually falls into your healthy tissue. But where your tissue is all like bad shingles, this liposome drug will fall into there. And then the cancer is always hungry. It'll say, "What's that? A jelly donut?" And you're like, "Yeah, it's a jelly donut." So then it opens up the jelly donut and you're like, "Surprise, you're dead." How about that? So it's like the Trojan horse. Does everybody see that? So how do we know to do this? Kind of like from studying viruses. So the emulation here is, we made, in some senses as quotes, the air quotes, right? We made like an artificial virus, but it's not a virus. But we made a drug that uses the algorithms of how viruses have been successful since the dawn of time. And we substitute the jelly in the jelly donut to actually cure diseases like cancer. And I have big, long I don't know, maybe in this series later on, I'll actually do just cancer drugs or something like that. The ones they always want me to do is cancer drugs and vacuum. So if somebody says vacuum or cancer drugs, then I automatically get volunteer. But then I had to do this top-down, bottom-up one because nobody else wanted to do it. They're like, "That one's really hard." And I was like, "I'll just go talk. I'm fairly entertaining." So there you go. So this is my presentation. What I wanted to do here, which I've done already, and I do in all my presentations, I do my presentation like in an introduction, and then I review it all the time. So I just told you what I'm going to do and did the whole thing, but now I'm going to go through and revisit it and fill in some more details. Does everybody see that? But really, that's what I wanted to present today, is those key things, and tell you like how a liposome works, and how I wanted to tell you about scale of virus, scale of a transistor, and the difference between top down and bottom up. Oh, I didn't say bottom up works on, you put chemistries together, usually at moderate energy levels or temperatures, and the chemistries have an affinity to self-assemble. So as like an engineer, you don't force them into place with energy. They just do what's conducive to them. A problem with that is that's kind of like hard to find, or the tricks that you can do are moderately limited. Does that make sense? So certainly as, I don't know what to say, tasks or manufacturing methods or whatever, you're all based on cell phone parts and computer parts. So that's all top down. But they do some bottom up stuff like organic LED screens. But, that's more, I guess, of an exception. I don't know to say that, but, there's more stuff that's top down, like transistors, than there is bottom up. Although you can make bottom up transistors, they just tend to be bigger. So I wanted to
I had a question based on that. I'm thinking when we say nano manufacturing, about traditional machine shop like thing, is the top down like taking a hunk of metal and putting chips out of it and making the part, versus bottom up like a 3D printing where you layer stuff on? Is that a good analogy?
I think that's a good analogy. And the one that I think about a lot, and this stuff's not true, they're just analogies like cartoons or whatever. I mean, they're helpers to help us get it. I think like nature is bottom up. You plant a corn seed, and then the roots are drawing out nutrients and placing them in the right part. And the only energy that they really have, which is not only, but they have the sunshine and the, the ambient temperature in the environment. And it's not like 600 degrees, but, it takes corn, 180 days to grow or something, depending on the corn or whatever, like field corn for horses or whatever. So it takes a long time for corn to grow because it's that. Now transistors are like, we do it, force the energy, and that work gets done in a shorter amount of time. Does that make sense? But I think kind of like a microprocessor, I'm not sure anymore, but they used to take like weeks to make. And that's just because there's 600 steps and you had to wait for the machine shop, like, the assembly line to catch up. So they do like wafer starts per month to see like how successful a company is or what their production is. So wafer starts per month, and it takes a while for that to work its way through. But semiconductors, et cetera, are relatively quick because the energy is like a delta function, it's compressed. And then when we have nature, it's rather slow and limited, so I don't know to say that because nature is bizarre. Nature's infinite.
Along those same lines, at least currently, the top-down method of machine shop is still used for mass production, but the 3D printing is just like one-off pieces. Is that still true in nano?
I would say that it's just like slower, and it's a different reference frame, like what you need to do, it's hard to compare like billions of transistors to things that are 3D printed. I don't know if there's billions of transistors made every day. I don't know if there's been billions of 3D printed objects since the dawn of mankind, number wise. And I don't know these things. You asked the question, this is what's going through my head, so yeah, they're like, it's comparing apples and oranges, top down and bottom up, but bottom up tends to be slower because you have to wait for the chemical affinity to lock in to do its thing, and then you're like forcing things with energy and top down. And then there's like laws of how things would fit together with self-assembly. And we take advantage of those laws and rules, like this thing sticks to this thing. For example, if I wanted to make an organic layer on top of some material, like gold, I might use a thiol, which is like a lollipop with a sulfur head and a polymer tail. So that lollipop will come down. Let me get a tax deductible teaching aid. So this is my lollipop. This is actually the spoon I just stirred and crushed my orange into my tea. But this is my sulfur head, and this is my polymer tail. And this costs $10,000, and that's what I'm going to deduct on my taxes this year. I'm just saying that to make it official. So anyhow, my teaching learning aid here, when this sulfur head sticks to gold layers like crazy. So I put it in, the tail won't go there, the head will. So then I have like blades of grass going here. Does everybody picture that? It looks like my surface is covered by this polymer hair. But now I have a polymer, which is made out of carbon and hydrogen, right? The CH kind of stuff. And what can I link to that biologically? Anything. That's the wild card. Does everybody see that? It's like a one-eyed jack in poker. You're like, oh, I'm playing this hand. I got me a one-eyed jack. So I'm winning poker tonight. How about it? So the thing is we can go from inorganic to organic with these linkages, and that would be self-assembled. And that would be like a self-assembled monolayer. But from that monolayer, now that polymer tail, the C's and H's, I can connect other, biological entities rather easily. Does everybody see that? And if I had some other layer, like silver, then I would have another lollipop, but the candy head would be different. Maybe like carbolic acid or something. So those things, silver carbolic acid linkage, they're big time. So there's rules of thumbs that we can go from one to the other. Does that make sense? So we could do something like, and this is true, if I wanted to do a cancer treatment drug, one of them is gold nanoparticles. So I put gold nanoparticles in a person where I inject them into a tumor, and the gold nanoparticles are kind of like a bell. They have a resonance. So resonance is vibration, right? So if I shine like or if I elicit, maybe is a better word, elicit some kind of energy, like infrared energy, maybe that'll be like the wine glass tuning fork. The gold particles will say, infrared, oh, I'm vibrating like crazy. And when they vibrate like crazy, they heat up. And when the gold particles heat up to like whatever, 110 degrees Fahrenheit or whatever, they're going to kill the tumor. Does everybody see that? But the problem is your body doesn't want to have gold in it. So what do I do to make sure the gold isn't taken out by your kidneys and all that other stuff? You would link some polyethyl glycol on there so that the body thinks that it's a piece of food and it leaves it alone. But still underlying it, it's resonant to that infrared wave. And now we can use that as an ablation technique or a heating technique that would kill a tumor. So those things are like cool. I like knowing stuff like that, That's really, so like, what's self-assembly good for? I could actually coat metal nanoparticles, make them look biological, and then I'll be able to use that metal thing for my task. And in this case, I was using it for heating up a tumor and killing cancer. So that's cool. I like that people were able to do stuff like that, beats radiation. I had that stuff like radiation. That is like medieval. That radiation is no joke. I'll tell you, I couldn't lift a gallon of milk and I'm a big boy. That took me down for a year. Yeah, that was really bad. So I'd rather somebody had the wherewithal, and that's what I hope the students do. They contribute to society and they're able to come up with stuff where you don't have to suck in 30 days of radiation because you want to do something else. That's pretty archaic. I hope there's a day where people be like, radiation, they banned that in every country because that stuff is foul. That's really something. And I was in such good shape and then I couldn't climb a set of stairs. I couldn't believe that. And just think, if you're not such good health, I was in my prime maybe, and then you get that. I don't know how people survive it really. That's bad stuff. So I'm glad to contribute and talk about nanotechnology, nanobio. And then my students write me letters when they get out and they're like, this is what I'm doing for this company. It's real exciting for me because I think I'm part of this. Well, I am. I'm part of this contribution of that. So that's really neat to be able to do that kind of stuff. So then what we're going to do is the outline here. We're going to look at microelectronics. And that was the transistor. Like I said, I already did this already. And deja vu all over again. And then we're going to look at the liposome thing. And that's really like the COVID drugs and the COVID and cancer drugs. So it's not even a BOGO, buy one, get one free. It's like buy it and get all kind of stuff free. How about it? So nanofabrication processing, what we want to do is we want to make, entities that are less than 100 nanometers or so. And usually when we do that, when we say like less than 100 nanometers, just like as a physics thing, below that level, things like melting temperatures, optical performance, biocompatibility, they all change. Let me wipe my lips off there. So anyhow, they all change. Does everybody see that? Like under 100 nanometers. So we get special things like gold doesn't look gold anymore. It looks green or blue. And that's kind of cool that it looks that color. But what might be neat is when it fluoresces like that, maybe we could do something like conjugate or put a self-assembled monolayer on the gold, put it in on the gold nanoparticles, put it in a patient, and then that surface on the gold sticks to a tumor. When it sticks to the tumor, when the surgeon goes in to cut the good tissue and bad tissue, they can have special glasses on and lights and say, hey, this is where the tumor ends. And this is where the good meat of the person begins. And naturally, they're going to cut a little good meat out because they don't want to leave any tumor in. But now what they do is they cut way a lot out, which is smart. But again, you pay the penalty because they're probably damaging you too much. Does that make sense? The goal of like a surgeon or cancer is to kill the cancer, but not kill the healthy portion of the patient. And that's why radiation is really bad, because it kills everything, right? You're just hoping it kills the cancer a little bit quicker than it kills the person, but it's about this close. So you don't want to have that. But if you could spot the tumor or be able to say where the tissue transitions, or there might be other cells that are spreading there, metastasizing to other areas, then you would be able to, a surgeon would be able to do a better operation and do better for the patient. Because after any, major surgery, naturally the patient is weakened, and you don't want to weaken that much, because they're trying to get healthy and they're trying to fight off residual cancer. So that's a good idea, to use markers to be able to know where to cut in a patient. Does everybody see that? So there's another BOGO, buy one, get one free example of where we would use nanoparticles with bottom up techniques to be able to site tumors in a surgical environment. And then these things vary broadly from nanoparticles or drug delivery, and that's what I'm talking about. The chemical catalyst, so we could have these as, things. A catalyst is something that's in a system, and what it does is it speeds up the system but doesn't get used in that system. Does that make sense? So this catalyst is a multiplier, but it doesn't get used up into that. So we could use that. We could use it for, guiding light and plasmons and waves. And we're working with somebody in another. I like the guy too. He's cool as hell. His name's Shaheen, and he's doing quantum, computing and quantum light kind of stuff. And he's just a really nice guy. He's a gentleman. So I like talking to him, and I have a little bit of talent in certain areas. So I help him out in his lab things and just helping him install a wet bench, or I had one that I had in storage. So I donated it to him and help him with connecting it to the room. I'm really good at like building labs and being a machinist. And I think that's my calling in life. So I'm doing them things, and I like to do those things, but I like to teach too. But I'm helping him out. He's really cool. So he's doing quantum, plasma, or, light and light wave controlling and ones and zeros with light. He's really interesting. He just got a big award grant I've seen this morning. So I'm helping him. We can do light signal processing, and we can certainly make those transistors for microprocessors, right? That was on my first slide. So it's all kind of different things. And this is really important. And I put this in the classes, and maybe since we're in this pandemia, I guess I've been watching some other language or something. That's what they call it in that other language or something. And I watch these people on there. Actually, it's a cooking show. And they talk about cooking and like my mother made. And they talk about that. And then they go to restaurants and review the restaurants. I think it's so interesting. And they're a couple, and they actually like each other, which is very interesting and unusual. And so I think that's really cool. So they review a bunch of stuff, and it's really entertaining. So they call it pandemia or something, but I think that's what it is in Polish, the word for it. So although I know a little bit of Polish, but Polish is a tough language, So anyhow, this is, if we look at a blood cell or a regular cell in a body, or a generic form, or maybe how fast is a car going on the highway? I'd say 70, and that's a decent number, right? But it's not true. It could be 55, it could be 80. But a comfortable number, I would say a comfortable number for a cell is 10 microns, and it's a nice even number. But if we look at a virus, it could be from 2 to 100 nanometers. So something like 60, 80 nanometers for a virus, that's the size of the COVID virus, and it's the size of the drug we're going to talk about today. And it's the size of actually the gate of the transistor. So everybody's in that world. So we're beyond that. And a nice number, it depends on your vision or how many carrots you eat, I guess. You can see down to about 30 nanometers, 30 or 40 nanometers. Does that make sense? If you have really, really good vision and you didn't get to the part where you have a gray beard and you need reading. I actually don't need reading glasses yet. It's like so crazy that I can still read and don't need glasses. But you can see down 30, 40 microns when you got real good vision, like thread and needle kind of stuff. And below that, you can't see. So you really don't walk around seeing red blood cells. You can see blood, the net of the accumulation of blood, but it's hard to see a cell. But you have like no chance you're below the optical performance range of light, because you can only go with about 1,000 times magnification when you're using light aided characterization equipment like microscopes. you can go about 1,000x. But to see viruses and stuff, you do need things like scanning electron microscopes. And what, in some senses, I think that I do is I work in the area of viruses, and I build things the size of viruses, and they're like a norm to me. Just like a carpenter, maybe a norm is like a 2x4 piece of wood or a 4x8 sheet piece of plywood or whatever. So those would be like, you know, guys that go to Lowe's in their pickup truck to go build a doghouse or whatever. Those are norm numbers. To me, I'm like all about angstroms and nanometers, and then I go from there. Does that make sense? And I usually go up to like microns. And when somebody says microns, I get a little bit nervous because stuff bigger than microns is too big. Because I build things out of atoms, and to build atoms to be microns just takes too long. So I'm more comfortable. People would come to me and say, build me something 100 microns or build me something 100 nanometers. I feel better doing 100 nanometers because 100 microns is just going to take me hours and hours and hours. The machines I have are geared to do nanometers and angstroms. The gauges on the manufacturing machines that I use are usually 10 to the minus 10. Like miles per hour on your car, I'm 10 to the minus 10 on the gauges. Does that make sense? Like 10 nanometers is a 10 miles an hour or something on a car, right? As an analogy. So I'm used to making things real small. Does everybody see that? So maybe a point here is, are these viruses in biology confusing? Yeah, and it always will be. I just can't believe the information that biology guys have to compress in their mind. And everything's just like one of 6 choices. And I'm like, no, semiconductors, quantum physics, we have one choice, and I'll show you the equation. It'll be 3 pages long, but there's one answer at the end. But the bio guys are like, no, it could be 6 different things. And if it's raining out that day, it might be 7. I'm like, no. So it's a little scary to me because I'm brought up in the inorganic world of semiconductors, Fermi levels, things like that, you know, designing Pentium chips, things that I did in the past. And things were, you know, pretty on mathematically, and bio's like wild card kind of stuff. And everybody has a different pH level, and people have more or less ACE2 receptors, and their blood's more or less acidic. And oh my goodness, they like to eat sea food, you know, seashells, so they got more zinc in them. Wow, you know, they're hogging on the oranges, so they got more vitamin C. So you can see why some people, you know, succumb in their age and their health of their lungs and stuff like that. But you know that the you know, saying a virus is going to make somebody infected, you don't know. Most of the people don't even know they had it, kind of. And I just had a friend die 2 weeks ago of COVID, but he was 86 years old. But man, one of the better guys I ever knew. Just such a good guy. So now I'll tear up. So anyhow, this is top down versus bottom up. So in top down nanofabrication, one grows and forces or deposits layer of material, and by some combination of physical and chemical methods creates the desired nanostructure, as you would make a statue from a block of marble. So we're like carving things out. Does everybody see that? And using a lot like a sledgehammer. So we're, you know, energy wise, especially energy wise with relationship to the size. This is like huge. Does everybody see that? It's like tons per square inch kind of stuff, because the things we're making, when we apply energy to such a small area, it's really tremendous, you know, constraint in a certain area of energy. It's huge energy. So I think that's kind of something to think about. And with, like I said, bottom up, it's kind of room ambient kind of energy and chemical affinity that makes those things together. So it's certainly more elegant and more time consuming, and the rules are rather limited. We force top down in some senses, and then bottom up, we allow nature to do what it likes to do in a timely fashion, whatever it thinks timely is. So we use these methods to make microelectronic chips. We use it to make sensors. We use it to make all kinds of different things. And what we do is we take material and then we pattern it, usually deposit, etch, pattern, deposit, so we go through a cycle and it's repetitive. And I think I mentioned here, I think I dropped that bit of information. A microprocessor might take like 600 steps, and when you look at self-assembly, I don't think any of them are like a dozen, kind of. They're rather simplistic, and you usually get things that like the products from bottom up tend to be more rudimentary and simpler. And things like microprocessor transistors, et cetera, they're just so big and insane, and 600 layers, and it's crazy stuff. But we're doing energy with that one, and then the other one's more simplistic. So in my mind, they're different because of how they're manufactured, or just the perspective of how we're forcing energy in, or how we're using energy allocations. So in bottom up nanofabrication, we start with small components, such as individual molecules or nanoparticles, and then we allow these to assemble together to grow and to grow out. So we can take a self-assembled layer like I described before, like maybe a gold nanoparticle, stick that lollipop on there, the thiol, then I have my carbon hydrogen tails, then my carbon hydrogen tails I can stick on other biomaterials. So I'm doing one level to a next level to a next level. But those levels have to have a next conducive, like Velcro that likes to stick to it and nothing else. Does everybody see that? So you have to have that allowed state, and it's difficult. And it takes a while for things to reach like a density, like for that grass to grow, for those thiols to line up. They take a while to grow. And like a lot of processes, they grow exponentially, and then they flatten out. And for you to get that last one takes you 3 forevers, right? But for you to get pretty much like 98% or something is moderately rapid. And then for you to fill in those voids at the end, it just gets more difficult mathematically, right? So those things are true engineering models. They're true certainly in self-assembly. So that's why we use self-assembly. And it's like a self-guided thing. We control those roles, and we would mix the chemistry in some fashion, and it would form a product. And they're a little bit, I think that's not used that much, but that's me. If I was a chemistry major, then I'd say my whole world is making styrofoam cups and PVC pipes and things like that. And that would be like maybe some form of self-assembly. But I'm looking at more, how would I make a smoke detector sensor? And I would automatically be thinking, and I don't care which one I would use, I'd use the most efficient one. I'd be thinking, I want to go top down, and I want to follow the semiconductor algorithms. So when we're looking at top down, here's some like crazy picture things, So we start with a material on a substrate, and then we add some material. We define that usually with lithography. And what lithography is, and I'm sure like Oscar likes to talk about that, we put down like a stencil, like cut out the letters of your name, and then we usually put a protective layer on a material. Then we put that stencil there, and we remove the protective layer, like the lithography mask. Then we take that template off, and then there's exposed regions. And then those exposed regions, we could do stuff like etch or add a metal, because the other regions are taped off with the lithography stuff. Does that make sense? So it's kind of like you cut your name out in some cardboard and put it on your mailbox and then spray paint. It would be a localized area of deposition. Does everybody see that? And the lithography process could be thought of as, your piece of cardboard that you cut your initials in, or whatever your name for your. So we subtract some of the material, and maybe we subtract it, not, certainly deposition is addition, but the areas that are exposed and other areas are protected, maybe we could dip it in something like an acid, and then the acid nibbles away at the stuff that's not protected, and then the stuff that's taped off doesn't get etched away. Does everybody see that? I thought about doing that myself, and I might do that just for like putting like symbols or like a jewelry thing, and like putting like initials or whatever on an axe, or making things like a beagle on a shotgun, pattern those things like as a jewelry kind of stuff. So I always thought when I was getting a little older, I'd like to do like engraving and make like oak leaves and all that other stuff. I think that stuff's beautiful. So I'd like to do that. I thought about buying a laser printer and doing lithography, and that would set the pattern, and then I could chisel out into the metal. I'm really looking into doing that. I'm excited to do that kind of stuff. I think that's artistic, and I really don't have any art. So I'm going to pretend that I'm an artist someday. So we do this, we repeat and we subtract. And basically what we're doing, we're putting these building blocks together in a predetermined way and maybe taking some in and out, and then we're building a structure. So what we basically do is we do the patterning mode over the course of a substrate, usually like a silicon wafer. Then we make deposit, which is an addition. We might etch and remove other areas. And then we might modify material by doing things like doping or something, like alloying in some ways. So we can change that performance of that material locally to do different things. And certainly that's what we're doing by entering N and P type dopants inside a transistor structure. We control their conductivity. So we're basically like gates in a waterway. We're saying open up here, and we direct the flow of electricity in different environments. And we can do that by controlling the material and acting the materials as gates or open gates or closed gates. And it's interesting that when we apply electrical bias, we can even change those performances or modify them in real time. So, by definition, transistors are active devices that we're actively controlling their material parameters by bias. So when I look at words, I like to look at words and definitions and see how powerful they are, and I'm fairly careful with my words that what they mean. So I always like to see something that says like they're active devices, and then sit around and say, what the heck does active device really mean? And an active device is like this tremendous concept of idea that we can dope things and control the conductivity and change the Fermi levels and all that other stuff. It's brilliant on like an artistic level, like Da Vinci kind of stuff. Just that word, is just enlightening. I think that stuff is cool, so I always like, words. Words are always brilliant. When I went to school, I went to classic old, Catholic religious school with nuns with habits on and stuff like that. They really did a good job teaching vocabulary. And we would just look at things on a really small level. And I think that aided me in being a teacher. And I always don't rush, and appreciate things. And they taught me that. That was a really good lesson. That was really good classic training in school, and I wasn't much raw material to start with. They really had some work to do with me. So they did a hell of a job, I think. So I really love nuns. So this material modification, and I respect them highly. So the material modification, what we're going to do is we're going to do like dopants. And then we have things like active devices, and just that concept of we took inorganic material and now we can make inorganic material in some senses like alive, and it can steer things and think. So that's something. It's like artificial intelligence and stuff like that. It's really, really dynamic to do this kind of stuff and think about, as a teacher, what you're teaching people. You're really opening up conduits for these people to do great things for society. So this is what we do. We do lithography, deposition, etching, material modification. But we can do like a few etchings and then one lithography. Then, so what you do is you do them in different sequence. And when you do them in different sequences and with different materials, the final product is infinite. You have all these choices in how you would do the particular procedure. When you change the procedure, you're going to change the device, like the steps and the sequence. So when you change the sequence, the materials, the energy levels in your recipes, you change the devices. So it's really like an infinite, skill or infinite platform to make things on the nano scale. So it's really, really interesting. And I can hear my voice cracking. It's going to give up you like whispering at the end. No, I don't have that much. It'll go pretty quick. So here's top down, bottom up. So those 4 steps, you can skip them, you can modify them, you can loop them around. So there's basically those steps to do a microprocessor plus cleaning. And cleaning's the most abundant step in making a microprocessor, cleaning the layers. But it's like 600 times that we're doing things, maybe even more. So this is what we're doing. We're going in this loop, but we can go backwards, forwards, skip a step, do all that other kind of stuff. But basically that's what we're doing. And we're going to look at the lab video later, and it'll show you, like Oster's going to take us on a tour and say, here's a sputtering tool, here's our wet bench, here's the AFM, SEM, just so you see how big they are and stuff. And then maybe it'll make sense with what I was discussing today. And I might interrupt in there and say, hey, that's a sputtering tool. That's a tool that we deposit metal, like for a gate on a transistor. So, and then it deposits at a level that it's as big as a virus, so that stuff is impressive. So we can watch that, and I might interrupt. You can certainly break in and ask questions about it when we get to the video part. So I wanted that to be fairly interactive. So let's see how this goes. Thin film will grow or deposit a film on the substrate underneath. So that's my starting platform. Usually like a transistor, it's going to be a silicon wafer, right? And it'll be P-type. And so I put it in a chamber. That's what that square is. And now what I'm going to probably do is apply high temperature heat and oxygen. I think it's really worth talking about, and I don't know if you would appreciate this comment or whatever, but this is a big comment in my mind as an engineer that processed silicon for decades. Silicon is king because silicon dioxide is queen, and the queen rules. The queen is the ability to have an insulating layer. So the reason why silicon is so important in the number one semiconductor is it has a native oxide, and it's mechanically mates with the silicon rather well, and it doesn't delaminate, and it's inexpensive, and we can grow it by heat, we can deposit it, we can sputter it, we can do it by gas. There's all kinds of different ways that we can have an insulator. So semiconductors are kind of cool, but really what allows us to utilize all the ability of the semiconductor is to have an insulator. And I don't know to say this, philosophical statement, but silicon is nobody unless it has its good friend silicon dioxide. So silicon dioxide is, I think, the key to the semiconductor market. I think that's, you can't have one without the other. So it's not like a choice or something. But I really think that silicon dioxide is the control, because we have other materials like germanium, but they don't have a good oxide. So they can really, they're kind of like a silicon kind of thing, group 4, but they don't do the things we can because they don't play well with the dielectric like silicon has its own. So really they're like a Reese's cup, like peanut butter and chocolate. They really go together. Or an Oreo, that chocolate thing with the mystery, who knows what it is, white stuff in between. And now we're coming up on St. Patrick's Day. So it'll be green stuff that's in the middle of the Oreo cookies. So who knows what that is? Only some mad scientists know what that stuff is. But it's really important. And the silicon dioxide is like, I just salute that. That's really important stuff. So we actually oxidize the wafers, and we grow this oxide from the silicon. And we generally do that at temperatures at 900 degrees C. So we all know to go from Fahrenheit to Celsius, we do 1.8 plus 32 kind of. That's kind of hard to do. Physicists will do that because they're diligent and they have a lot of time. Engineers would say times 2. So I'm like, wow, 900, that's like 1800 Fahrenheit. And I know I cook my chicken at 350. That's a lot of Fahrenheits. Does everybody see that? So that's crazy hot. And metal starts, you'll have like thermionic emission, and like metal starts to glow red, like in your toaster oven or whatever, around 600 degrees C. So this is like crazy hot. Does everybody get the scale on the hot? That's crazy hot stuff. It's like double hot wings or something. Does everybody see that? Triple hot wings. So that's really hot. That's hot, hot stuff. So here's my thin film, and I apply oxygen, but oxygen would actually, it would make a native silicon dioxide, but quit at about 40 angstroms or so, and it wouldn't have enough energy to diffuse and then to grow. So at room temperature, we wouldn't be able to really get, or certainly a good oxide film at that point. We need to have really high energy. Like I said before, 900 degrees is just, Celsius is crazy. And that's where you grow the best oxide. Actually, at that temperature is a pretty good sweet spot that most people would recommend that you would grow your oxide at 900 degrees C. Does everybody see that? That's a really good temperature that most people would respect. And now what we did is we have my oxide on there, and I'm pushing the buttons and kind of waiting for that to happen. Nothing happened. So now I'm going to do patterning, lithography. And lithography, like I said before, is like cutting your name out on a stencil, then being able to either like spray acid down or deposit metal or something like that. So it's a patterning thing. And what we wanted to do is, and we can all see that, you know, on your phone, you have like microprocessors and stuff. They're as big as your thumbnail. And on your thumbnail, there's going to be 1 billion transistors. They have to be walled off from each other so they don't short out. And that's what silicon dioxide does for us. And that's why it's really important. So we spin on a resist, which is like our tape. You know, that's our protective layer. So we spin that on, and it's an organic polymer, and it's light sensitive. And now what we do with lithography, I'm waiting for these steps. I align a mask, and the mask is really our pattern. So that's our template, like our piece of cardboard with our initials in it. So I align the mask, and I'm aligning it to some pre-existing thing. And we see these openings in there, and they're going to be our drain and our source, kind of like we're making one individual transistor on this diagram. But of course, we're going to be making, you know, thousands and thousands at a time if we were doing this on a microprocessor on a chip. But this is the focus that we're doing one. And this was going to look somewhat like the original transistor that I had on my cover sheet. So now I expose it with light, and usually the mask is in contact there so we don't get the light to spread out, but what the heck. So here's the light comes down, it goes through the glass part, but the part that's black there on the mask is chrome, and that's going to reflect the light back up. So only the light where there was an opening in the glass goes down. And now where that light hit into the photoresist, it changes the chemistry of the photoresist. So there's a light chemical reaction. We can do it one of ways, negative or positive, but most of the time it's positive. And where the light hits the polymer, it's going to break the bonds. So that's the one we're going to talk about today. There's a mirror image of that, but I don't want to confuse people or myself. So then the chemical bonds are altered in the exposed region. And I think altered is good, because if it was positive, it would break them. If it was negative resist, it would link them. So I changed that. You see where the photoresist is, it became grayed out. So now that's like weakened. And now what I'm going to do is I'm going to put it in developer. I like how that goes as a wave. I didn't do this. Somebody else did this. I can do some things like this, but I never tell anybody I can, because then they'll have me doing it. Sometimes I like doing it. Other times I feel it tedious. And so now what I did is I selectively removed that photoresist in one region. Does everybody see? And these are the top-down methods I'm doing. So now that where it says thin film, I could do something like etch that away, or now I can deposit maybe aluminum over the whole thing and it'll be on the photoresist, but then it won't stick. If I put it in acetone, it'll lift the photoresist off, and then it would selectively just go where the thin film is. So I can deposit metal, or I could put it in like an acid, and the photoresist will protect the thin film, but where there's a hole, the acid will eat that away. So I have multiple like choices when I did this patterning. Now this allows me to do other techniques. On this one, I'm going to etch. So in a plasma, I'll put a bias on here, and I'll make an excited gas. And the gas itself has some constituents in there. It's going to have kinetic energy from like ions. The ions are going to come down on the surface like a sandblaster. And I'm also going to have chemistry like an acid. So it's really crazy aggressive and fast because I'm doing this like an acid sandblaster. And what do I want to do? I want to make money. So time is money. So I'm just not doing acid and I'm not just doing sandblaster. I'm doing both at the same time. And it gets to be a synergy and really fast and really accurate, because I'm not going to talk about it now, but I might do a presentation on etching. You can make three-dimensional things in a substrate, three-dimensional objects, like a wine glass or something, make like an image of a wine glass inside something as big as a virus. If you said that in the Middle Ages, they'd burn you at the stake. That's like heretic kind of stuff. You can do that and teach that. That's cool. Does everybody see that? It's like how many angels are on the head of a pin kind of thing. That's really cool. And that's the power of etching. And it's the power of having two dials. We would have kinetic energy, like a knob going in this direction, and chemical energy is like a knob going in this direction. Kind of like an Etch-a-Sketch. You can have an up and down knob. And what can you draw with an Etch-a-Sketch? Almost anything. So then we do a surface modification, and this is the dopants. So we can do things like we would get like arsenic, and we would use arsine, the gas form. Why? Because we're doing nanotechnology, and when we want to do an atom at a time, a gas molecule is discrete. Does everybody see that? So gases are like a good choice because they're atomically small. So we would take something like phosphine, which is phosphorus, but in a gas form. Also something they use like phosgene in World War I to kill people, right? So things like arsenic gas, phosphine gas, they're way wicked stuff. Does everybody see that? They use bromine too. So all the most popular dopants in semiconductors are all gases that are banned to the Geneva Convention from World War I. There's a little trivia for you. Or you have to teach safety when you look at nanotechnology, or know about it when you go into semiconductors, because that's actually the stuff that they use for real. And I must have had a big day on YouTube yesterday. I was actually watching some, like the biggest crater ever in World War I think it might have been I don't think it was Argonne Forest. It was some other place. And I never knew about that. And they were talking about gases and stuff like that. So I thought that was interesting kind of stuff. So I must have had a big day on YouTube last night. I don't watch TV, so I look at YouTube once in a while. So the ion implanter, what we're going to do is we're going to take ions and accelerate them, and we're going to push them in like this. But we only want them in a local place, the drain and source. What they're going to do is they're going to wind up in the resist in the areas that's protected. And we're going to wash that away. And now we're locally able to make a drain and source. Does everybody see that? So this is the material modification thing. And this is called doping. And it's done with an ion implanter. So what's an ion implanter? We take a gas, we ionize it, which is by definition removing an electron. Now they're charged particles. Since they're a charged particle, they want an electron more than anything else. We put a real, negative field down here of electrons, and what they'll do is accelerate into that electrical field, just like gravity kind of stuff. And they'll come smashing down with like 50,000 electron volts of energy, and they'll be able to go into the lattice. So it's like shooting a shotgun into, plywood or something. So we're shooting this dopant into there. Does that make sense? And how we can get a handle on it is with charge. So the nature or the definition of the charge is an ion. So we ionize the gas, and then we put a really big negative bias here, and that positive gas will come down and accelerate, and it'll actually force its way into the wafer. Then it's not in the right crystal lattice site. We're going to heat it up, and then it'll be in the right place, and it'll contribute to the conduction in that area. And it'll conduct better holes or electrons, and that's why we care about N and P type, because we're steering electricity through the system. So there's that in my surface. That's ion implantation. I think this ends a little bit early. Remove the photoresist. And now I have that. I think this is done. Oh, I did the thermal anneal. This is to put the dopants into the lattice site, into the crystal lattice distribution of the silicon. So I do that heat, and now I made a drain and source. So it said it's complete, but actually what I would do is, see where it says the words thin film? That purple, that's oxide. On top of that, I would put a metal, and that would be the gate. And then I'd put wires into the drain and source, and then that would be my transistor. So there should be another step where we put the gate on there. So this is bottom up. And basically we do a couple steps. You know, what we're going to do is we do these sequences, but there's allowed states. And I look at it as like Velcro that only sticks to certain Velcro. So we do the building block, and then we do the self-selection. And then like that layer that you put on there, like the polymer tail, now that becomes your building block. So then you add to that, then you add to that one, then you add to that one. So really it's only 2 steps. You just grow something, grow it and grow it out, keep on growing it out. Does that make sense to everybody? So there's not like patterning or whatever. It's just growth. And then the new growth becomes the old growth, and then to grow again and grow again. And that's basically, you know, that pictorial. And this is the thing that I show them and we do in class, and I have labs on. You might want to adopt it in your course. We make things called liposomes. And what a liposome is, it's a self-assembly unit, and it uses a lipid bilayer. So that lipid bilayer looks like my $10,000 tax deductible learning aid here, my teaspoon. On the end here, what I'm going to have is a phosphate head. Phosphate's like water. That's why they're in soap, right? Or the nature of soap, Tide and stuff like that. So here's the phosphates, and then it's going to be a fatty tail. Does everybody see that? So phosphates like water, fats don't. Phosphates like water, fats don't. So what we do is, if we put this into water, all the phosphates would point to the water and the tails would point in. And we would get what's called a myocell. So they would look like a star. But what we can do is, in a certain configuration, we can have a lipid bilayer to where we get, oh, I need another spoon. How about my penknife? So we have these tails, and we would have a head, and the 2 tails go together, and then the heads point out. Can everybody see that? So that's called a lipid bilayer. And that's really neat because that's your cell membrane in you. This is how your cells are made, out of lipid bilayers. So this liposome is kind of like a clone, copy, plagiarization of you, of your cell membranes. But it's the size of a virus. Remember that scaling chart that I gave you before? So we're making a liposome, and it's 100 nanometers or 80 nanometers or something like that. But basically what we do is we take these assembly units, lipids, not teaspoons, but and they're made out of egg, usually like egg yolks, or maybe soy powder, soy. And if we put them into water, they're going to form an energetically favorable sphere. Does everybody see that? That's the self-assembly. We don't need nature. It's like phosphates like water, fat doesn't. So that's the magic here. We didn't force it. The rules were, or the chemistry is, that it's going to form that. So then on the inside, when we do this, and I'll show you the manufacturing method down here, how we put it together and make it. So I'll show you how we make it, but I'm going to hand wave till then. What we do is we put these lipids in water, and they're going to form these spheres. But we just don't put them in water. We put them in water that has like poison in it. But when it forms a sphere, it traps the poison in the middle. Does everybody see that? Does everybody see it kind of looks like a jelly donut? And the poison is now the jelly. And the donut part, you know, like the flour part or whatever, flour, yeast, eggs, right? In your, when you make a donut, that's what we have. And then on the outside, it has those proteins and linkers. That's going to be like our corona. That's going to be our self-assembled layer that we put on top. And that's going to direct this drug to where we want it to go, or hide it from your kidneys, because it says, what the heck is a liposome doing in here? I'm going to put you in the kidneys and the bladder and we're out of here. But you don't want that to happen. So we put a sugar on there, polyethyl glycol. They call that PEG, PEG. And then your body looks at it and is like, damn, it's a sugar donut. Let it go. I like sugar donuts. You like sugar donuts? I like sugar donuts. So you're like, white blood cells, leave that alone. It's a sugar donut. So then it can actually go in your system for a number of days. And then where your cancer is defective, it'll fall in those nooks and crannies. And then your cancer says, yum, yum, a donut. And it opens it up and there's poison in there. And then you don't have to go to radiation. So there's the end of the story. Happy ever after. How about it? But the corona right there below that, it's the same thing. It's a liposome model, or liposome is a model of the virus. On the inside is not poison, but it's an RNA piece that goes into your body, and your body takes it in and says, oh, here's a program that I have to run. Usually your body's going to do something like, oh, I'm going to make a blood clotting agent, or, you know, your body has to carry out these feats, or I'm going to make my mouth water, or it's going to do some certain other biological entity for you, right? But then it says the program here is make other viruses. And that's what the virus does. Does that make sense? Your cells are relatively dumb. They just say, here's a program, and the program's inside of my cell because it had the right, like, garage door opener. And I'm going to let it in and I'm going to do what it tells me because I'm a liver cell, you know, I'm a kidney cell, I'm a whatever, a lung cell. I'm going to do that. But the virus actually unlocks parts in your body that are rich in ACE2 receptors, which a lot of times your throat, your lungs, kidneys, the base of your skull. And that's why people exhibit problems in those areas if they exhibit problems, because those become contaminated. And then the real problem is your body overreacts. If your body just says, it's cool, I'll kill it, then you're okay. But a lot of times your body says, I'm going to panic and then just kill the person. And that's when it gets iffy. And then you get swelling in your lungs. And if you didn't smoked or something, you lose your lung capacity. That's what actually is, you know, mostly deadly in just a casual conversation way about the virus. So the virus itself is really the liposome. Does everybody see that? So for years and years and years before we had the pandemia, you know, I taught viruses and virus emulation. And I never knew that it would be, and I still don't know if it's interesting, but then people ask me about it. And I'm like, no, I don't know. I fix chainsaws, man. I don't know nothing about that. Because then you talk about it too much and it doesn't do any good. It's just like, I fix chainsaws. That's what I do for a living. So here's the liposome cutaway view from somebody, from some girl. I should have her name on her. She's from the Czech Republic. And she made this drawing. I thought it was real cool because I like the colors. But this is a cutaway, and we can see the lipid bilayer. And then that little crystal in there is our poison of choice, or whatever we want to deliver. In the COVID, it would be the RNA. And then that other fur on the outside is the stuff that would direct it to a place we want it to go. Is everybody seeing that? So that model, which I think is important. Engineers have to have structure, model, and analogies and algorithms. Does everybody? I think that's bread and butter. I think that's what you do. So this is kind of neat that we copy this. Does everybody see? And they could, like, in the end, they have things that are like little, I don't know, Y's or V's. Those are protein linkages. And I guess like the pink fur on there would represent the polyethyl glycol, and that's going to be stealth. If you put a naked liposome in, it would be out of your body in 20 minutes. If you put the sugar on there, that pink fur, and it's probably not pink, but you put the pink fur on there, it'll stay in for a few days. And you need time for it to drop into, at least in what I teach with the mindset I'm looking at a cancer drug, it would go into the defective endothelial cells in the cancer region. How about that? That's neat stuff. So this is the membrane structures, and see, your cell is made out of these lipid bilayers. Does everybody see that? And then it has like garage doors open on it, side doors, windows. And what happens is you have like a key on there, or a lock. And then the COVID comes down with the certain protein, it makes a bond and it does some energy release, and then it'll open up the doorway. Does everybody see that? So now what we want to copy is, what's the doorway to liver cancer? The doorway to pancreatic cancer? Or what's the doorway? I want to send in a blocker to RNA to block the COVID RNA, which is kind of like modifying your DNA. Well, that's a little scary. Just saying. I'd rather have the antibodies than modifying my cellular machinery. Wow. That's something. So anyhow, that's how it works. Does everybody see? So the COVID's going to go to these ports, link up with them because they're the right key, right lock. So a lot of times in biology, they would say certain, like biology guys get like t-shirts like this written on there, like lock and key protein interaction or something like that. So lock and key kind of stuff. Does everybody see that? Or central dogma of biology kind of things, you know, RNA, DNA kind of stuff. So they have their own set of t-shirts, right? So this is the phospholipid structure, and this is the basis of the cell membrane. And it's also the basis of the liposome, and it's the basis of the COVID virus. So it works on with self-assembly. This is the bottom up part, that the phosphate likes water, fats don't. So then the fatty tails go together and the phosphates point out, and then we can have an aqueous core. So that's how we make our donut. Does everybody see that? That's our donut of choice. So here's the liposome, and what we do is we have the lipid bilayer. We can put water or solid pieces in the core of the lipid when it's formed. And then if we wanted a fat drug, we can trap the fat drug in the tails. But the volume in there isn't so much. That's a little bit hard to do. So you're better off with an aqueous drug. And then on the outside, we can put proteins or sugars that make it stealthy. Sugars generally stealthy, and proteins can be a directive. And a lot of times they say like nano robots. I think that's what they're talking about. This will go to a certain place. Does everybody see that? But not like movies from the 60s robot going in your body stuff. You know, this is it. Does everybody see? But this is not that anybody even wants to know. I think everybody in the world wants to never say the word COVID again or think about COVID. Everybody wants to put their mask on one big pile and burn it, you know. But if you wanted to know about COVID, there you go. Then forget about it tomorrow. Like in that Men in Black thing, get that light and just forget about it. Certainly that's true. I had enough of COVID myself. I'm about done. I'm done. So I just want to go hang out. I want to talk. I want people to say hi to me in the store. People wear these masks and they don't even hold the door for you anymore. I just think that people are, you just could like, just be friends. So that's all I have. So you can go buy this stuff. You can go to like Sigmund Aldrich and you buy this powder, like the liposome powder, and it's made out of eggs or soy powder. So it's like a lipid base, and you can refine that, right? So you can buy it. It's not like unheard of or Star Trek technology or something like that. And what you do is you get your lipid powder, like your cake, and then you put it in there with a liquid. Then you put your drug kind of stuff in there. You put it in, then you stir it up, and it's going to form these spheres because they're energetically favorable. This is our self-assembly. Does everybody see? That's our self-assembly. It's going to form all these spheres. An issue, though, is the spheres are going to be this big distribution of sizes. And for the most part, they're going to be too big because the currency of a cell likes to take things in under 100 nanometers. Your average liposome, when you make it in this method, is going to be thousands of nanometers. So what we have to do is we do this process where this is how it forms. So we put the powder in and the water and the drug, and it's going to peel off and form little bubbles. Does everybody see that? So we're putting in like a powder, shaking it up and get they have them like protein drinks, put the powder in and some milk, and you get this foamy milkshake things that taste like sand. It's like one of those. Then what we do, the spheres are all different sizes. We get a strainer that's 100 nanometers or 60 or whatever. We get a screen. We put the juice in one side and a pocket in the other, and we go like this, back and forth between the screen, kind of like a pasta maker, like we're making rotini on a big piece of pasta, and we're squeezing it in and out. And then what we're doing is we're forcing those spheres down into being the size that we want, like 80 nanometers or whatever. So a job in nanotechnology might be to make 80 nanometer screens. Does everybody see? And this is a tabletop one on there. And what you see the guy's hand just for scale, but in industry, they have real big ones. But I bought one of them. I have one of them in my lab in the back room. And every once in a while, when I go back in there, I find it. I put it in a box and I'm like, there it is. And then I lose it again. And then I come back, I'm like, where is it? But I have it all videotaped. But I'd like to bring it in for show and tell, but we don't have students anyhow. But so I have it kind of. So when I make my liposomes as raw, they're all these different sizes. And the one that I want is the SUV because it's the currency that the cell will accept. The other ones, they're like, that's too big. I don't like it. So they're wasted. Does everybody see that? So now what I do is I take this whole Gaussian distribution of sizes and I put it through my strainer pasta maker. And what I'll get is, oh, I'm done. I don't have that extra picture. What I'll get is I'll get all SUVs. And I think that it takes 7 passes or something. And then you'll have like 95% of that thing. You just can't do it in one. But if you did like 7 or 11 passes, then you're going to have a really good sharp peak Gaussian distribution of that population. And you have to, because when you give this as a drug, that's a controlled dosage. Does everybody see that? So you have to have this well-defined currency so that you know what you're going to get is a medical reaction. Does everybody see that? So if they do have this, like in Europe, they call it a different name than the US one, and they made it like 10 nanometers bigger, but it's basically the same thing. And then patent lawyers, whatever, they gave them the patent, but they have to change the dosage, but basically it's the same thing. But because they made it a little bit different diameter, they were allowed to call it a different name and get around the patent that was here, you know. So they sell this under a couple different names, but it's basically the same. I don't want to get sued by some patent lawyer, but it looks the same to me, you know. So here's the self-assembled layers, right? And we talked about this before. You could have like a gold interface. And then if you got this thiol thing, which I showed you, what's this up to $5,000 teaching aid so far? I'm going to take off of my taxes next year. So those will actually, the lollipop head will land on there. And now we have my polymer tail. And the biology, that's a wild card, right? Those C's and H's, oil or whatever, you know, you have C's and H's, you got all biology there. You can do anything with you want there. Gold, you're kind of, what can I stick to gold? Actually, gold's like a noble metal. It's hard to stick anything to it. Luckily, we have my good friend sulfur, but then I go from there to like instant, I can do whatever I want biologically, like put a protein on that, C's and H's. Really easy to do. Does that make sense? That's an interesting field. And here's a set of rules. If I wanted to have a surface like platinum or something, then I would use a thiol, or I'd use phosphine, or I'd use an isotriol. I'd use any one of those. Does that make sense? And if it's blank, I didn't do the research on it, so I don't know. But the other ones work or don't work according to some papers, or that paper. And then I had a teaching assistant that I worked with, Dave Johnson. He was he still is. He's a good guy, smart, hard worker, man. He helped me look all this stuff up too. But if you have certain surfaces, there's rules that you can only use other surfaces to stick to it, like that Velcro. So it's not like unlimited. And you got to go by like what nature gives you. It's like a real well-defined game. Top down, you force the game into whatever. It's like you're playing cards and you get a marker and say, oh, I got a joker. You know, you change the cards. You're forcing energy. And bottom up, you have to play by some really strict rules. Top down, you're like, I'm going to bend the rules. I'm going to apply a lot of energy. Does everybody see the difference? Top down, bottom up. And so then the liposomes and the viruses can open gates. We talked about that. So you guys take care, and I'll talk to you later. Sounds good.